And with that, we'll move to the question and answer portion. I believe our first question is from the Johnson Space Center.
Mark Carreau, I'm with the Houston Chronicle. In some of the literature, you described an expectation of 45 or more Earth-like planets as a result of this study. And I wonder if you could explain how you reached that estimate.
Yes, I would be happy to do that. Basically, what we do is we look at the capability of the mission. What can it do in terms of photons and length of mission? And then we also look at the stars themselves. So we ask ourselves, if we were to put a planet around each of these stars in a habitable zone, what would the instrument be capable of finding? And the answer is about 50 Earth-sized planets, if most of them have such an Earth inhabitable zone.
50 Earths, 50 oases, 50 dreams. In 2009, a remarkable experiment was attempted. The idea was to launch a meter-sized telescope into space, one dedicated to searching for Earth-like planets. Worlds with the same size as our own, receiving similar warmth to our own, and orbiting stars similar to our own. NASA's Kepler mission was one born of ambition and drive, a testament to the human will to reach out to the stars, a product of our relentless curiosity about our place in it all. Even before it delivered a single discovery, the very idea of Kepler, the audacity to ask such questions, reflects the very best of humanity. So much hope rested upon the shoulders of that little telescope, flung out into the dark on a fragile evening in March 2009. It was a dream, decades in the making. Principal investigator Bill Borucki had devoted much of his professional life to designing and studying his concept, one that first took root in a seminal paper in 1984. In 1992, he proposed to NASA an approximately meter-sized space telescope dubbed FRESEP to search for other Earths. But NASA rejected Borucki's dream. In 1992, again in 1994, as well as 96 and 98, it was only on his fifth attempt in 2001 that the refined mission concept, now dubbed Kepler, was accepted as NASA's 10th Discovery-class mission.
Liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Kepler is NASA's first mission capable of detecting Earth-sized planets in the habitable zones of stars like the Sun.
The primary question that Kepler's interested in is, what is the frequency of terrestrial planets in our galaxy?
If we find an Earth in the habitable zone, I'm going to pop a bottle of champagne and celebrate. That's what I'm going to do, personally.
From the very beginning, Kepler was pitched as a mission with a clear primary objective: to measure what fraction of Sun-like stars have Earth-like planets. This fraction, which is often dubbed Eta Earth, is one of major astrobiological importance, representing one of the parameters in the famous Drake equation. Kepler couldn't find life, but it could find the possible seats for life. But it's crucial to understand that Kepler's quest for Eta Earth was never purely an act of scientific altruism, knowledge for its own sake. Its import extended far beyond mere intellectual curiosity and had direct engineering ramifications for future missions. You see, Kepler's results would set the stage for future space telescopes that might one day go on to look for signs of life around such worlds. For Kepler was always conceived as a stepping stone, a rung in a ladder of NASA missions that might one day go on to result in the detection of life elsewhere, each generation contributing a piece to the puzzle. Successor missions to Kepler are in the early planning stage right now. Concepts like Lijoi and Habex aim to block out the glaring light of stars with sophisticated suppression technologies in order to one day photograph those distant pale blue dots. The capabilities of these missions are strongly constrained by their physical size. The bigger the telescope, the further out into space they can peer, capturing ever more stars, ever more Earths. Of course, large space-based telescopes are incredibly expensive. For example, the recent James Webb Space Telescope clocks in at approximately $10 billion. Now, science teams are fully aware that astronomers will not be given infinite funds to look for alien life, and so we have to limit the size of our telescopes to realistic budgetary constraints. For example, with Lijoi, the team proposed two variants depending on budget constraints. First, there was the 15-meter class high-end concept, and then a more modest, scaled-down 8-meter version. This roughly halving in size leads to an approximately halving of the number of stars that could be surveyed at the sensitivity needed to detect Earth analogs. So in this way, Kepler's results would directly impact the design of these future space missions. For example, imagine that nearly every Sun-like star has an Earth-like planet around it. If so, we would only need to build a fairly modest-sized telescope, one capable of surveying out to about 10 light years or so. If, on the other hand, it turns out that Earths are incredibly rare, that means that the nearest Earth would be correspondingly much further out, perhaps hundreds of light years, thus requiring a much larger, more expensive telescope to one day take a photograph of it. And right back, in the very first pre-launch Kepler press briefing, Professor Deborah Fisher clearly articulated just how important Kepler was when it came to the design of these future space missions.
Deborah?
Okay, well, this is my chance to say that I see Kepler as a component of a whole continuum of missions, right? The radial velocities took the very first step and showed us that planets even existed around other stars. Kepler, by virtue of the statistics that it finds, is going to tell us how frequent the occurrence of Earth-sized, Earth-mass planets are, and then that's going to tell us what the next step should be. So I think from Kepler itself, no, we don't get that information about whether or not there's life there, what the atmosphere is like, or anything else. The goal, right, the 15-year, 20-year vision of astronomers, and I would bet of NASA, is to someday take a picture of a pale blue dot orbiting a nearby star. But there's no question that this is going to be a key driver, right? The frequency of Earths that are found by Kepler are a key driving point for NASA missions to ultimately do exactly what you're asking about, to find out whether there's life or signatures of life on other planets.
It's been over 12 years since Kepler launched and 8 years since the primary mission ended. By dozens of metrics, the mission has been an extraordinary success. It would be an understatement to say that exoplanetary science has been transformed by its results, revealing thousands of new worlds, new types of planets, a detailed understanding of their demographics and properties, and unprecedented insights into the stars they orbit. You know, much of my early career was built upon the shoulders of Kepler data, as were many of my colleagues. Kepler trained an entire generation of exoplanet astronomers. In so many different ways, it was an extraordinary success, and I can only express my gratitude to Bottaccini and his team for enabling his magnificent vision. And yet, as astronomers look to the future, to these life-seeking missions, we have to revisit Kepler's original goal to detect and count other Earths. From the very outset, there was a sense of optimism about the mission. As highlighted at the beginning of the video, Bill Bottaccini estimated that Kepler could find around 50 Earth analogs. I suspect that when NASA saw that number in the original proposal, it gave them some comfort. After all, even if Bottaccini was wrong by a factor of 10, that would still ensure many detections. The justification for this estimate of around 50 Earths is detailed in a series of papers and conference proceedings in the years building up to Kepler's launch, including a recent 2020 retrospective that Bottaccini authored. The team arrived at this number by first assuming that every star has an Earth-like planet around it, a simple assumption born of the Copernican principle. However, Kepler could only detect planets if they had the right orientation to eclipse or transit their star. That was, after all, the method it was using to search for planets. For Earth analogs, that corresponds to a geometrical probability of 1 in 200. So if every star has an Earth around it and we want to detect 50 of them, then we would need to observe 200 times that, so 10,000 stars, in order to overcome the odds. However, even that number is not enough because, of course, not all stars are sun-like, nor are they all bright enough for us to have the necessary data quality needed to detect the tiny signature of an Earth-like planet. This led the team to conclude that at least roughly 100,000 stars would need to be surveyed in practice, with the final design settling on 170,000 stars being simultaneously observed. The prediction of 50 Earths fluctuated a little over the years building up to the mission, depending on what one calls an Earth, the evolving number of and types of target stars, and the continual refinement of their prediction models. For example, in the original 1996 proposal, when Kepler was called FRESIB, around 50 Venus-Earth analogues were predicted, of which 21 would technically be the Earths. By 2003, that number had slightly evolved to 25. Where the definition was now more clearly defined as a planet being between 90 to 120% the radius of the Earth and within 20% of the Earth's orbital radius. Now that orbital range isn't exactly the habitable zone, a topic of great debate and constant revision, but it's a sensible proxy for Earth-like conditions around Sun-like stars. The next year, a similar number of 25 was predicted, but now with a warning that this number could be halved if binary stars can't support Earths. In the final pre-launch calculation, which was documented retrospectively in Baruchi's 2020 paper, the predictions were broken down now by star type, with 6 predicted around the more massive G-type stars, 7 for the lower mass Gs, 14 for the high mass Ks, and 16 for the low mass K-type stars. There's an additional 67 predicted around the red dwarf stars too, but sticking to the sun-like stars, the ultimate goal of Kepler, we have a total of 43 habitable zone Earth-sized planets, approximately equal to the 50 number that Baruchi cited in that press briefing. These predictions were the results of hundreds of simulations, decades of planning and testing. They had gone through peer review and, of course, ultimately received the endorsement of NASA itself. Now, the reason why I emphasize this is that those estimates seem perfectly sensible. But, of course, here today, we can look back with hindsight and ask how well do those original predictions stack up against what was actually found? And more importantly, does that comparison potentially hold any lessons for us here today? So let's peel back the Kepler results and look at what was found. Because dozens of Earths seems like a lot. Did we really discover that many? So what did Kepler find? The easiest way to look at Kepler's results is to head over to the NASA Exoplanet Archive, linked to down in the description. It's a wonderful service that provides an interactive catalogue regularly updated by NASA staff and serves as the canonical database for astronomers. Let's begin by removing any planetary candidates that have already been flagged as a false positive. Those are known to be bogus signals. This gives us a list of 4,724 viable planetary candidates. Now remember that Kepler's goal was to survey Earths around Sun-like stars, so let's filter the catalogue down to stars with surface temperatures consistent with that of G and K-type stars. That leaves us with 2,913 objects. Now Baruchi defined an Earth as being between 0.9 and 1.2 times our planet's size, so applying that filter dramatically cuts things down to just 333 objects. But most of these are too close to their star to be habitable. Baruchi considered an Earth analog to be a planet with an orbital radius within 20% that of our own, which would mean that the planet receives between 70% and 156% the flux from their star that we do. Applying that as a further cut, we're left with just 3 planetary candidates. KOIs 549901, 717901, and 723501. Alright, it's not the 43 that we were promised, but 3 temperate Earth-sized planets around Sun-like stars would still be incredibly exciting. However, all three of these remain unconfirmed at this time, and as far as I can tell, there exists very little published research about these objects specifically. So let's do some real-time science right here and take a closer look at these objects, starting with KY 7235.01. In this case, there actually is a literature reference by a colleague of mine, Guillermo Torres, who has been one of the architects behind the Kepler team's work to validate their planets. In his 2017 paper, there is a brief mention that Torres will not consider 7235 in his paper because it is a known false alarm. The candidate has an orbital period of 300 days, and so it undergoes just 4 transits during the entire Kepler mission. Looking at these 4 transits, we can perhaps see why it was flagged as a false alarm. The first transit looks pretty good, but then the next one 300 days later is apparently missing, perhaps falling inside this data gap. The third one looks reasonable again given the noise, but then the 4th transit doesn't show up as expected. A simple explanation to this is that the period is in fact not 300 days at all, but rather twice that, 600 days. With that doubling, to my eye at least, the transits now look sensible again, and so we could perhaps argue that it should be rescued. However, by doubling the orbital period like this, we end up pushing the planet into a wider orbit around its star, so much so that the amount of heat received from its star would drop by a factor of 2.5. That decidedly pushes the planet out of Bottaccini's Earth proxy zone and leaves us now with just 2 candidates, KOIs 549901 and 717901. Both of these are challenging signals to work with, right at the hairy edge of detectability. They're listed as having signal-to-noise ratios of 7.6 and 8.2 respectively. Now, that might sound like a lot, but in Bottaccini's original estimates, he predicted that a planet would have to pass a threshold of 7 in order to have a 50% chance of being detected. So, on that basis, these objects actually just creep through the door. Yet more, the 3 transits of KY 717901 produce a strange-looking transit shape when added together, raising some suspicion about its reality. Going further, astronomers Chris Burke and Fergal Mullally have both led recent papers that argue that long-period, low signal-to-noise transits just like these are often being erroneously claimed to be high-confidence planets. They show that these kind of signals can easily be caused by instrumental effects happening on board the spacecraft itself, such as electronic noise or thermal effects. In what surely must have been a hotly discussed paper within the Kepler consortium, they showed that 2 of Kepler's most prized validated discoveries, the famous Kepler 452b and Kepler 186f, should not have been called validated planets by the Kepler team because they don't pass the 99% confidence level necessary to warrant that label. And I'm sure some of you probably recognize the names of those objects because they have of course featured heavily in the news as being claimed Earth twins.
NASA scientists think they have discovered the most Earth-like planet yet. For now, you can just call it Kepler 186f.
An amazing discovery by NASA to tell you about. The space agency says it has found what it's calling Earth's cousin, the most similar planet to our own they've ever found. As NBC similar to ours, it's generating a lot of excitement about the possibility.
All the science geeks, whoa, are they excited about this one? Earth 2.0, they call it. NASA has discovered Earth's bigger and older cousin.
Despite all of those headlines and media attention, actually neither of these make our list of Earth analogues because Kepler 186f orbits a red dwarf star, not a sun-like star, and Kepler 452b is too cold, receiving about half the amount of radiation from its star that the Earth does from our sun. But I suppose this is somewhat irrelevant anyway because their low signal-to-noise nature, as shown here, puts them deep in this red danger zone for being an instrumental artifact, a ghost in the machine. As an aside, science communication faces a real challenge here because a press release announcing a newly discovered Earth-like planet is far more clickbaity than the subsequent articles by Mullally and Burke that argued that these planets may not be real after all. We often hear about the former, but not the latter. There's an imbalance. Even today, scrolling through YouTube, you can find dozens of videos presenting Kepler 452b as if it is a real Earth-like planet, when really that's not reflective of the current state of knowledge. And it's a similar story for our friends KOIs 549901 and 717901. They are both low signal to noise and exhibit just a few transits, meaning that they are also in great danger of being bogus signals. Now, this certainly doesn't prove that these signals are not real planets, but it does give them something like a 50% chance of being bogus. So, like tossing a coin twice, we perhaps end up with just one of these, but plausibly, zero. So where does all of this leave us? Well, 12 years after that original prediction of something like 43 detected Earths, we are left with 0 validated examples and only 2 iffy contenders in the running. This lack of any Earth analogues ultimately explains something that we've pointed out here on this channel in a previous video. You see, the efforts to statistically validate the frequency of Earth-like planets show radically different answers, varying wildly by factors of up to 100. Eta Earth could be anything from 100% to barely 0%. And remember that these estimates are being made by NASA scientists, the world's top exoplanet astronomers, astrostatisticians, all using the exact same data set and arriving at staggeringly different answers. Now, when it comes to closer in planets, the agreement is really strong, but for Earths, the fact that Kepler doesn't have any confirmed detections means that all of these Eta Earth calculations are forced to make extrapolations about the planet trends, which are inevitably highly sensitive to the assumptions that go in. Now, rather than argue about the value of Eta Earth specifically, what I really want to just understand here is what went wrong. How did the original NASA Kepler proposal predict around 50 Earths, and yet we essentially got none? Certainly, we could broaden our net here and include the red dwarf stars or a more optimistic habitable zone and start counting more planets that way. But I think that really misses the point, because here we have tried to stick as closely as possible to the same definitions and criteria that Bottaccini originally used in his pre-launch prediction papers, rather than constantly changing the yardstick. In terms of trying to understand the shift in numbers from predictions versus reality, I think that's the only fair way to go, and it raises a puzzle. Why did reality not match pre-launch expectations? Perhaps it would have been less painful had we never hoped, never dreamed of those 50 Earths, but the disappointment persists and we're left wondering what happened, what went wrong. There's 3 primary ways that the prediction could come out way too high like this. 1. The assumptions about the telescope's performance may have been too optimistic. 2. The assumptions about the intrinsic noise levels of stars may have been underestimated. And 3. The assumption that every star hosts an Earth analog may have been unrealistic. The first of these would perhaps be the most surprising, because the team tested their cameras on the ground extensively before launch and they found they performed as expected. One way we can investigate this, though, is to measure the amount of noise in each star that Kepler actually saw. This somewhat depends on what timescale you're interested in, but for the 6-hour timescale, which is typical of Earth-like transits, we can see a diverse range of noise levels for all of Kepler's stars, shown as a function of how bright the star is. Not surprisingly, the fainter the star is, represented by the higher numbers here, somewhat confusingly, the noisier the stars tend to be. Now, this noise could be due to all sorts of things, including the stars themselves. So instead, let's just look at the noise level of the quietest 1% of stars as a function of stellar brightness. This is the so-called noise floor, the level that the telescope simply cannot perform better than, limited by the optics and the electronics of the spacecraft itself. Now, back in 2008, Bill Bottaccini kindly emailed me his predictions for the Kepler noise floor to help me in estimating Kepler's performance when it came to exomoons. Overlaying that noise model, we see really quite impressive agreement. Overall, we'd have to conclude that nothing seems amiss here. This factor cannot explain our lost Earths. So this leaves us either with stellar noise or a genuine paucity of Earth-like planets as our possible explanation, or perhaps some mixture of the two. Now, the Kepler team were well aware of the importance of stellar noise right in the very early documents about the Kepler mission, and they used extensive studies of the Sun to calibrate their expectation. But this was challenging because at the time, no one had ever really monitored stars at the ridiculous precision level that Kepler planned to do so. Thus, we just didn't know how variable they truly were. At the time, it was reasoned that the Sun was presumably a typical star, and thus studies of the Sun could provide this value. Another example of the Copernican principle in action. Now, fortunately, they found that the Sun was quiet enough that it really shouldn't be an obstacle for discovering other Earths. It had a typical variability of about 10 parts per million. Now, for context, the Earth transiting in front of our own Sun causes an 84 ppm dip in brightness. So 10 ppm is fine. That really shouldn't be an issue. It's more than 8 times smaller than the signal that we seek. Going back to our graph of the noise levels that Kepler actually saw, we can see that the stars are very often much noisier than that flaw, the limiting capability of the telescope. Presumably, most of that excess noise is coming from the stars themselves, but perhaps the telescope also misbehaves for some of the stars more than others. Let's try removing the giant stars on this plot, because they're notoriously noisy stars. Now, this helps a little, but even just with the dwarf stars, which includes our Sun, the noise levels are much higher than that 10 ppm level originally predicted. In fact, if we include the amount of excess noise for each of these stars here and look at the distribution, we can see that the typical noise level is about 100 ppm, a value that exceeds the Sun's by a factor of 10, and even exceeds the signal strength of an Earth transiting the Sun. On the face of it then, this seems like a possible explanation. We took the Sun, assumed it was typical, and later discovered that it was in fact unusually quiet. Whilst in of itself, this is incredibly interesting and something we have discussed on this channel before, it still leaves us with a problem that the detection of other Earths is far harder than we originally imagined. Perhaps, in hindsight, this could have been determined ahead of time by observing a small set of stars with Hubble. That's really the only telescope capable of doing what Kepler can do, but hey, hindsight's 20/20. To close the case, let's ask what would happen if we repeated Borucki's original yield calculation, but used the actual noise values that Kepler saw rather than the assumed pre-launch values. And let's follow Borucki's calculation and assume that every single star has an Earth-sized planet around it, and that those planets are at the correct distance from their star, such that they receive the same flux from their star that we do from our Sun. Let's give our fake planets random inclinations and orbital phases, and then use a detection emulator to determine whether each one of these would be detected or not by Kepler. I have to especially thank Jessie Christensen for her help and advice on creating a realistic emulator here, carefully calibrated by the Kepler data. Finally, let's run the simulation 10,000 times over to get a sense of the spread of values that one might expect. It took me about 2.5 weeks to code, debug, and run the damn thing, but hey, this is cool worlds. We expect only the best right here. So finally, just 2 days ago, those simulations finished and revealed some really intriguing results. Going from the lower mass K-type stars to the higher mass G-type stars and splitting them into the same groupings that Borucki originally used, the prediction changes from the original 16, 14, 7, 6 to 6.5, 5.2, 1.3, and 0.4 Earths. Together, this equates to a drop in the total from 43 to just 13. And crucially, amongst the entire class of those G-type stars, which of course includes our Sun, the most common outcome of these simulations was that just one Earth analog detection was made, even assuming that every single star has one. Let me say that just one more time to be totally clear. If every single G-dwarf star in the universe has an Earth analog planet around it, then we would have expected Kepler to have most likely detected one example of such a world, just one. That's of course a huge drop from the original prediction of more than a dozen, and I haven't accounted for binary stars here that would likely pull that number down even more. So how do we make sense of this? What are the consequences of these revised predictions? Well, of course, to some degree, this is going to depend on how much we believe the reality of those two candidate Earths, KOIs 549901 and 717901, which orbit a K and G-type star respectively. But I think the most important thing here is that regardless as to the reality of those two objects, the simple fact that we predict so few detections, even in the scenario of ubiquitous Earths, means that the Kepler data is, unfortunately, just not as constraining as was originally hoped during the conception of the mission. In the case of the G-dwarfs, the fact that we expect just one detection when all stars have Earth analogs means that the data really don't constrain E to Earth, whether KOI 717901 is real or not. But for the K-dwarfs, things are a little better here, where we expect 11.7 detections and see only one iffy example, consistent with either a low E to Earth value or technically even possibly 0%. But look, these are small number statistics and are consequently subject to large uncertainties. In short, resolving the nature of those two planetary candidates is certainly going to be useful information, but it's not really going to resolve the fundamental problems in play here. Like it or not, we are stuck with ambiguity.
I have dreamed a dream. But now that dream is gone from me.
In the end, what does all of this teach us? Look, the purpose of this video is not to try and derive some new value for E to Earth. That's too ambitious even for a Cool Worlds video. Rather, what I'm hoping this exploration provides is some insights to you as to why it is that the exoplanet community are arriving at such different values for this E to Earth parameter. The truth is that the data simply isn't constrained enough to precisely tell, given the noise levels that we're faced with. That ambiguity might be considered good news in a way. After all, it permits the possibility of plenty of Earths out there still. But on the other hand, it's quite possible there are hardly any Earths out there. And as another caveat, of course, remember that in this video, we have been defining Earth analogs strictly as Earth-sized objects receiving similar warmth from their star that we do. But many such worlds could be more like Venus than the Earth. Determining what fraction of these are truly Earth-like is an entirely different matter. To finish, it's worth coming back to what Professor Deborah Fisher spoke about towards the beginning of this video, that the results of Kepler would directly inform the kind of mission that we build one day to take photos of pale blue dots.
But there's no question that this is going to be a key driver, right? The frequency of Earths that are found by Kepler are a key driving point for NASA missions to find out whether there's life or signatures of life on other planets.
For one of these mission concepts, Lijoi, their 2019 report predicts that 28 temperate Earth-sized planets could be surveyed with the 8-meter class scope, and that would become 54 with the larger 15-meter version. Indeed, 28 was presented as a minimum useful number because even if they found that none of these planets to be truly habitable, they could still derive a constraining upper limit on the frequency of habitable conditions. But in reading those numbers, I can't help but be reminded of the original Kepler predictions because they are, after all, eerily similar to the same kind of numbers that Baruchi calculated many years ago. And makes you wonder, could history repeat itself? Indeed, the fact that there is no consensus on E to Earth is an obvious problem for such mission concepts. In the Lijoi report, the team assumed that 24% of Sun-like stars have Earth-sized temperate planets, but as we've already seen, that's not widely agreed upon and may ultimately be unknowable from present data. And crucially, if the true rate is lower than that which they assume, the 8-meter design might not be large enough after all. So, which size mission will eventually fly? Both Lijoi and its cousin Habex were major topics of discussion in the recent Decadal Survey. That's a once-per-decade report published by senior members of the astronomy community that highlights the top recommendations to federal agencies like NASA for future missions and funding priorities. And in that recent report, one of the major recommendations was that a hybrid mission combining elements of Lijoi and Habex begin development, aiming for a 6-meter class design. The tone here is that it's early days and a lot of development is still undoubtedly needed. But the fact that an exoplanet imaging mission, one purpose-built to look for other Earths, has emerged of one of the Decadal Survey's top recommendations is a major boon for our field. It provides the community with leverage to go out and argue and lobby for such a mission concept in the future. I'm genuinely thrilled to see that, and I do not envy the mighty challenge that the committee must have faced in trying to forge this report together. And yet, if I'm being honest, the idea of a scaled down version of the smaller Lijoi concept, that does somewhat worry me. This thing will not be cheap, estimated at $11 billion, and it's going to be a hard sell to come back to NASA a few years later and ask to do it all again, but just slightly bigger this time. Personally, I'd rather that we end up over-engineering the thing rather than under-engineering it. On the other hand, the 8-meter version is estimated to cost up to $18 billion, and the 15-meter version more like $24 billion. Now, these costs are so high that it's very difficult to see how NASA could ever afford them given their current budget. And so in that light, how can the Decadal Survey possibly recommend a mission that they know NASA cannot afford? And together, this leaves us in a precarious situation.
The quest stands upon the edge of a knife. Stray but a little and it will fail, to the ruin of all.
You know, the numbers are tight here. They're balanced on a knife edge. Even a single misstep could jeopardize the dream. And we've seen that. We've seen with Kepler how when the instrument was pushed to its limits, it manifested unanticipated artifacts, how we underestimated the stellar noise, and how our optimism about the prevalence of Earths all served to truncate our dreams. They all conspired to lose us those 50 promised Earths. None of this is really the fault of the designers. They were pushing the envelope of what was possible from day one, and I have the utmost respect and gratitude to everyone who made it possible. But I think there's a chance to both celebrate Kepler's legacy and achievements, but also learn from it. Let's make sure that we give ourselves plenty of margin for the unexpected, because I fear that we may only get one shot at this, at least in our lifetimes. One chance to get it right. Perhaps in the end, in order to keep the dream alive, we have to be willing to dream big. So until next time, stay thoughtful and stay curious. Thank you so much for watching, everybody. These videos are a huge labor of love for me and are enabled thanks to the support of our donors, like our latest donor, Gary Canterbury. Thank you so much for helping us out, Gary. If you too want to support the Cool Worlds Lab, then be sure to click the link up above. And until next time, have a great day out there.